Hello! This video is the first one in a course on probability and statistics that I teach at Queen's University Belfast. Within it, I will explain what these two subjects involve and how the study of probability theory differs from the study of statistics. In particular, and by the end of this video, I would hope that you should be able to explain the difference between statistics and probability theory, and that you should be able to explain the various operations that we can perform if we are given a data set. Let's start by dealing with the central problem that the field of statistics endeavours to solve. Suppose we have done 100 experiments and that we have obtained the numerical results shown on this slide. The objective of statistics is to make sense of this data. There are various ways that we can do this. We could, for instance, make a visual representation of the data by drawing a graph like the one shown here. On the x-axis of this graph, we have the numerical index for our experiment, and on the y-axis, we have the particular result that was obtained. There are some things we can see more clearly. For instance, we can see that the number 4 does not come up very often in this experiment. And it is always worthwhile to draw graphs like this because our eyes are better at spotting patterns in visual representations of data than they are at spotting patterns in tables of numbers. Really, however, drawing this graph has not given us a clearer sense of what the data represents and what it means. What then should we do to make sense of a table of experimental data such as this one? Well, there are three options that you probably already know about. Option 1 is to compute the mean. For the particular data set shown here, the mean is 2.27, which was obtained by adding together all the data points that we obtained from the experiments and then by dividing by the number of experiments that were performed. We express this procedure of calculating the mean mathematically using the expression shown here. The xi values in the expression that we are summing together are the results from our experiments. x1 is thus the result from the first experiment. x2 is the result from the second experiment. x6 is the result from the sixth experiment. x13 is the result from the 13th experiment. xn minus 1 is the result from the penultimate experiment, and xn is obviously the result from the final experiment that we performed. Notice that when we talk about the results from experiments, i.e. random variables, we use capital letters. Within statistics, small letters are usually reserved for the parameters of functions. Calculating the mean might seem like an obvious thing to do because it is familiar. The mathematics that explains why the mean is a useful number to compute is actually quite involved, however, and we will return to this idea later in the semester once we have a little more probability theory under our belts. A more obvious thing to do is to note that our experimental result is always either a 0, a 1, a 2, a 3, a 4, or a 5. We can thus count how many times each of these numbers appears in the dataset. For instance, if we consider the number 4, we see that this comes up 4 times. The number 4 thus appears 4 times in this dataset. We can do this for each of the 6 possible values that our result can take, and we get 6 numbers, which we can store in a list. We can even plot a bar chart like this one that shows these 6 numbers. On the x-axis of this figure, we have the 6 possible outcomes for our experiment, and on the y, we have the number of times that each of these results came up. We can, furthermore, introduce a symbol for the 6 quantities that we have computed and plotted in the graph. Capital N, capital X equals small x, is the number of times our experimental result, capital X, was equal to a particular small x. In other words, nx equals x is the frequency with which we obtained the result small x when we did the experiment. We have thus seen two of the options that we have for dealing with the data. We can calculate a mean by adding all the results together and by dividing by the number of experiments, or we can accumulate the frequencies for each of the possible results from the experiments. There is still one final option that we have for dealing with the data that we get when we perform a series of experiments, however. We can sort the data into ascending order as shown here. As you can see, in this sorted list, each pair of adjacent results, xi and xi plus 1, are either the same or xi plus 1 is greater than xi. Sorting the data is useful, as by looking at the value in a particular index in the list, we can make a statement about the whole dataset. For example, this dataset has 100 points. If we thus look at the 50th value in the list, we can say that 50% of the points in this dataset take a value that is less than or equal to this number. Alternatively, if we take the 25th value, we can say that 25% of the data points are less than or equal to the value here, 1. We can even draw a graph like the one shown here that has the index in the sorted list on the y-axis and the outcome on the x-axis. The result is that the quantity on the y-axis of this graph is the quantity indicated by the mathematical expression shown here. The values on the y-axis are the percentage of points, the capital X's, that are less than or equal to a particular small x value that is shown on the x-axis. We can thus see that roughly 20% of the points are less than or equal to 0, and that 40% of the points are less than or equal to 1. We thus have three options for analysing the data that we obtain by performing a series of experiments. We can compute the mean, we can calculate the frequencies with which we obtain particular results, and we can sort the data and thereby work out how many of our results are less than or equal to a particular value. These three operations perhaps allow us to better see what the dataset looks like, but they still tell us nothing about how the data was generated. In other words, they tell us nothing about the particular phenomenon that generated the dataset. This is where probability theory comes in. In probability theory, we generate mathematical models of idealized datasets that are fully understood. We can then take the data generated from these idealized models and the data generated from experiments and perform these three operations that we have discussed at length, namely calculating the mean, sorting the data, and counting the frequencies. We can do this for both the real data and the model data. We can then perform a systematic comparison between the results from the model and the results from the real world, and thereby infer whether the model gives a good description for what has been observed in the experiments. This business of constructing models of idealized datasets and of calculating means, frequency tables, and sorting them is what is done in the probability theory that we will spend the first semester studying. In the second semester, you will then learn how the comparisons are made between the model data and the real data from experiments. This part is the statistics, which we will not look at in the first semester. Nevertheless, I thought it was important to explain here what the two parts of the module are about, so that you have a sense of where we are trying to get to by studying all this probability theory in the first semester. To summarize then, this module has two parts, a part about statistics and a part about probability theory. Probability theory is about constructing mathematical models for idealized datasets, and we will spend the first semester studying this. The statistics part, meanwhile, which will be introduced in the second semester, is concerned with comparing model data with real data, and thus with understanding the nature of reality. Within both these fields, there are three operations that we can perform on a dataset. We can calculate a mean by adding all the points in the dataset together and by dividing by the number of data points. We can count the frequency with which each possible result appears, or we can sort the data into ascending order. I hope that all this is reasonably clear. The computer programming exercises should help when it comes to reinforcing the three operations that we can perform on datasets further. Also, as you study the rest of this course, try to think about how these three ways of viewing datasets relate to ideas such as the expectation, the probability mass function, and the cumulative probability distribution function. Good luck.